Hello students, this is Professor Strawn. I just kind of wanted to go over a couple of items I typically see students struggle over as we go through the early weeks of this material. The first one is this concept of what we call similar triangles. And essentially what we mean is we're going to have two proportional triangles that are essentially, in this specific case, we're going to say they're right triangles. And what we're saying is that since these are similar triangles, if let's say this label these sides here, and that's a big C and a little c. What we're saying is these are similar triangles if angles 1, 2, 3, let's say this is 4, 5, 6. We're saying that these are similar triangles if and only if angle 1 is this one right here is equal to angle 4, and angle 2 is equal to angle 5, and angle 3 is equal to angle 6. All right, we're saying that if the inside angles are the same, that these are similar triangles and they're going to have a certain kind of properties. And essentially what we're saying is that the ratio between the sides are going to be the same. Right? So in this particular case, we'll say that, if we take the ratio between side big A and little a, that's going to equal the ratio of big B over little b, which is going to equal the ratio of big C over little c. Now let's take an example out of the book and let's apply this, right? So in the book, it says that we have a silo structure that's got an unknown height. So from here to here, we're going to just say that's an unknown height of h. And we know from this center point to the edge of its shadow, from here to here, we know that that's 24 feet, right? And it's going to have an imaginary hypotenuse right here. And we're saying that that is a right angle. Now, in the problem, it says that there is a pole that is perpendicular to the ground that has a height of 4 feet. And it has a shadow of 3 feet. And then where it has an imaginary hypotenuse. And when we say perpendicular, it's got a 90-degree angle. So we know that in this particular case, we're going to make the assumption that because they are right next to each other, the sun's over here in one particular area, they're close enough to where we can assume that the angles are going to be the same between the shadow, for the hypotenuse parts. We're just going to make the assumption here. So now let's redraw these into triangles, right? So let's call this one triangle 1. With a leg of h, another leg of 24 feet. And we're going to have this smaller triangle over here for the pole. We're saying it's 4 feet by 3 feet. The way that we kind of solve this math out here is we're going to say that the relationship between the height of the silo and the height of the pole, so the ratio should equal the ratio between the lengths of the shadows. So big shadow over little shadow, so it's 24 divided by 3, right? So then this becomes h over 4 equals 8, which then this becomes h equals 32 feet. And there's your solution for this first problem. Now for this next problem, what I'm kind of wanting to look at is solving for complex geometric shapes. Right, and the first one that we're going to do is we're going to say that I'm going to have a shape that's a square, and then it's mainly a square, and then we're going to assume that this is a perfect circle, although it doesn't look like it. It's going to have some ellipsis point to where the radius from here to there, the radius is going to be equal 1/2 of the side, right? So we're going to say a square, so we're going to say that these sides are all equal to each other and that the radius is equal to 1/2 of the side. So essentially what that means is this particular shape right here, this kind of lined out area, is we're going to postulate is a half circle, albeit it doesn't actually look like one. So now in this specific thing, we're going to say we want to find out what is the area of the green lined in space. What is the area? What is the area? So step one, what are the equations that we need? Well, we need the equation for the square, right? And that's really easy. We know that that's essentially the equation for the square. So the area of the square is going to be side times side, or sides squared. Now, we only want to know what the area is of the green shaded part. So essentially what we want to do is we want to find the area of a half circle. Well, we know that that's equation 1, right? So then we know that we need the area of a 1/2 circle, right? So we're going to start with area of the circle, I guess. We'll just write that over here, area of a circle. We know that the area of a circle is going to be pi r squared. Well, we only need 1/2 of that, so we'll just essentially divide that by 2. So we're going to say that area of a half circle is 1/2 pi r squared. Well, we know that r equals 1/2 s, right? So essentially, if we wanted to further break that down, you know, it could look something like this. You know, 1/2 pi times 1/2 s squared. You know, then we could take that out. You know, multiply those out, and essentially just becomes 1/4. But we'll just leave this like that for now. Or we'll just go back to, you know, this is the equation that we want to focus on here. We'll put this off to the side. We'll cover it up a little bit. We'll rewrite our problems. Hopefully you can still see all that. All right, so now we're saying is what is the total area of the square? Well, we know that we're doing a subtraction, right? We're taking away a certain amount of space. So we're going to start with the a of the square, right? So we're going to say side square, but now we're going to take away this half of a circle, right? So we're going to subtract 1/2 pi r squared. Again, you know, and if the problem in the quiz or the exam tells you need to simplify it towards all terms of S, you would need to essentially replace R with the 1/2 S, and then you essentially move on from there. But in this particular case, this ends up being our final solution. Now this equation right here, you could put in any number for this and fill it out, and it will give you that surface area. And the key to solving geometric shapes is how do we take different sets of functions, in this specific case, 2 different areas. We can add, subtract, multiply, divide to kind of get what we're looking for. Now, I want to look at essentially one more problem. Now, the next shape that we wanted to try and do is we're going to solve for the area of a pyramid. I'll do my best to draw a pyramid that's easy to see. Hopefully that you can see that. Now we're going to kind of break this down into a few different, values, right? So let's kind of mark this out. If we go from the top and we let gravity do its thing and we essentially let it drop a pendulum, it's going to hit some point, the center of this square, assuming that the pyramid is square. In this specific case, we're going to say that the bottom of the pyramid is square. And we're going to just call that some origin point, or O, right? Now, if we go along the line from there to here, we're essentially just going to have some value that's essentially 1/2 of the distance of the side, right? And we're going to call this point right here from the origin to the middle of this part, we're going to call this point A. Right, so this point right here, we're just going to call that point A. And I'm going to have to go over my own number. I don't know how well you can see that, but I just drew a line from the top. It's supposed to be across the face, right, from this top point that we're going to call point B. Right, we're going to bring that down to here. And so what we kind of made is in the middle of this pyramid, this 3D structure, we're going to take like a section of a right angle, right? And it's key that you understand that that's making a right angle. Now there's a point to where we're going to try and summarize some of these values, right? Where we say that from the line segment from B to O, right? So this top part to down here, we're saying that that's the height, right? And from some line segment from B to A, from point B to point A, we're going to call that side S. And then we're going to say that this side from that corner to that corner, right, or I guess we'll just try it over here, from over here, is going to be side A. Right, so there's 2 things that we have to start with, right? And the equation in your book, it starts with the area of this pyramid is going to be A squared plus 1/2 PS. So now what we're saying is, let's break this down. This part is essentially the area of the square on the bottom, right? And then this part right here is the area of the faces on each side, right? And we're going to then further break that down to where this value P, I'll change the color so it's easy to see. This value P right here, this value P is going to be equal to essentially the perimeter of the base, right? So essentially P is going to be 4, P equals 4 times side A. All right, essentially we're wanting the perimeter of the base. Now this S, what is this S? This S gets a little bit tricky, right? We're saying that this S, we're just going to draw it down here. S is going to be equal to, what we're going to look for this S, right, is we're essentially trying to find this value right here, this I guess the length of the side, right, is what we're looking at. So, you know, if we go back to Pythagorean's theorem, right, and we'll just kind of redraw this pyramid out. Let's just start a new piece of paper so it's easier to see. Bring that over here so you can still see it. So what we're going to say is, we're going to say that we're going to have, redrawing this, there's your height, there's the center point, and then that's the face of the outside, right? Or essentially the line segment B to O. That's this outside part right here. We're going to say that that's the origin, and then this part right here is going to be point A, and that's point B, right? So that's essentially side S. So in this specific case, you're going to be given a height, and you're going to be given the length of this side, right? So we can say that, you know, this bottom part right here, right, if we're trying to find that, let's just write it in the Pythagorean's theorem. So we'll say that, you know, we'll call this S, and we'll call this little b for base, and we'll call that h for height. And we're going to say that S squared is going to be equal to b squared for the base, and we're going to add that to height squared, right? And then solving for S, essentially we're saying that S is going to equal the square root of the base squared plus the height squared. Now in this specific case, we know that, going back over here, that from the origin to this side point B, it's half of the length of side A. So now this essentially can become S equals the square root of 1/2 A side A squared plus height squared. That's what S is. And then we can take all of this value and we can essentially plug it back in. So you solve, once you solve for S using these values, you essentially plug it back in to your total area. And so we go back over here, you know, we'll write it in red, the area of the square, right? A squared, because you're looking for the area of the square, plus 1/2 of the perimeter, right? Perimeter, which we know is 4A, right? 4 times the length of the side, times S, right? S being the square root of A divided by 2 plus height squared. And that is how you solve for the surface area of a pyramid. All right, so the next thing that we kind of want to talk about is using something that they call the trapezoid rule. Right, and so we get into the fancy. What this means is we're going to have some kind of a structure of varying sizes, and we're going to take known points. You know, we could take a point here. We could go, let's see, 1, 2, 3, 4, 5, 6, right? And we're going to essentially have 6 sides, so we'll just call this one, I don't know, we'll call this one D1 or D0, D1, D2, D3, D4, D5, D6, right? We're going to essentially start with this shape, right? And the goal of the trapezoidal rule is we essentially want to find a pretty close value for the average inside of this, right? So it's not going to be perfect, but we're going to say we're going to find something that's close enough for us to work with for planning factors or whatever, or where we have the ability to have a decent margin of error, right? So in this specific case, going to the textbook, what we're looking at in the fun equational form, right, is that the total area of this particular shape using the trapezoidal rule is going to be equal to some delta x, which we'll go over that in a second, divided by 2, divided by y1 or y0, sorry, plus 2 y1 plus 2 y2 plus 2 times y3 dot 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 2 y n minus 1 plus y n. So what this means here, right, let's kind of break this out. So what is delta x, right? Let's change colors to make this simple. What is delta x? What is this part right here, right? So delta x is essentially the distance between these spots, right? So we're going to say that this distance is delta x. In our case, to make sure that this math works out, is we're saying that all of the distances between these known points right here are essentially going to be the same across the board. It's going to be equal. So the distance from here to here is delta x. That's also delta x, delta meaning the difference between, right? And we go across the board. Some applications of delta x, you can essentially say that it's more of an average, where you can look at, you know, measurement. You measure all of the deltas. You can solve delta 1, delta 2, delta 3, delta 4, delta 5, delta 6, and then you could just average all that together to create an average delta x. But in this specific example, and what you're generally going to say, delta x is really the distance between essentially these two values. So the absolute value of d2 minus d1. And we're essentially just going to say that that is going to be even across the board, although it doesn't look like it. Now what does this mean, right? When we come over here and we say that, you know, you got y0, you know, y1, y2, and I even wrote it up here, d0, d1, d2, d3, d4, d5, d6. What we're saying is that this value, so this line right here, we're going to say that from this point to that point inside of this space is going to have some kind of a length, right? So there's a magnitude or a length of d1, and there's a length of d0, and so on and so forth. So in this particular case, we're going to say that these values right here are essentially those values of lengths right there. right? So we're going to use it interchangeably. You can see it in L0, L1, L2, L3, L4. I mean, there's a lot of different ways you could look at it. I mean, you could even see it as, other values, but essentially we're saying these are these measured lengths. These are known lengths between the two. Now, make a point, right? We see that Y0, there's no 2. Whereas, Y1, Y2, Y3, all the way up to Yn minus 1, we're saying that there's a 2 times in front of that. And then you have Yn, which there's no 2. So like in this particular example, what we're saying is your total area is going to be some known value that's going to typically be given to you, delta x divided by 2 times, in this specific example, we're going to replace the y's with the d's, d0 plus 2d1 plus 2d2 plus 2d3, wrap it around, plus 2d4 plus 2d5 being your last value minus 1. So the next one over, there's going to be a 2 there. Now this last one, right, this last d6, there's not another measured distance or length across the board. We're just going to call that one d6. And that's it. You plug in the values, let's say we were to give you that's a known length of 0, that's a known length of 2 meters, 2 meters, 5 meters, 12 meters, 6 meters, 8 meters. You essentially just plug it into this equation and then and solve for A.